Hello. So today I'll be talking about some of the math that I've been diving deep into within the last few weeks in terms of linear algebra and some preliminary stuff. So I'm going to try to make this concise because what ended up happening is I shot a 2-hour video of me explaining all these concepts, and then I tried to convert the Zoom file and it got deleted somehow. And I can't figure it out. So this is my second iteration, and this time I'm less motivated to make a 2-hour video. And I also think it'd be a good challenge to try to make it more concise and just more understanding in the time that I have. So I'm going to start off with talking a bit about how the scale of data types works. And it starts off with a scalar, which is essentially just a number. And you can see that it is represented with a lowercase letter, and it's essentially a real value. So for instance, one scalar is 1. And this is known as a zero order tensor because it has 0 dimensions. It's not something that's put into brackets. It's just something that is literally just a number. The next part are vectors. Vectors I will be explaining in a bit more detail because throughout the courses that I have done in terms of preliminary stuff and linear algebra so far, I've worked with the D2L.ai textbook. I've worked with the 3 Blue 1 Brown linear algebra and calculus playlist, and I've also worked on the Coursera course by Luis Serrano for deep learning AI. And through these courses, they've explained all these concepts in very different ways. The D2L.ai textbook is focused a lot on the mathematics of it, the numbers behind it, whereas the 3 Blue 1 Brown and the Coursera course are more focused on the intuition in terms of graphing it out and visually representing, for instance, how a matrix can actually be a linear transformation. So what I'm going to do now is introduce vectors, but I'm going to introduce them in a way that will be quite familiar in terms of graphing for intuition and numbers based on whatever people's needs and likes are in terms of learning. And then I'll be going deep into other stuff and higher order dimension data. So in terms of vectors, vectors usually have two properties, magnitude and direction. If you want to look at it from a graph standpoint, let's say you have one vector that is this right here. It's 6 and -2. So the way to think about this is because every vector has a magnitude and direction, you can think of the first element as x and the second element as y. So this first element will be how far you go at the x-axis, and this will be how far you go with the y-axis. So if you wanted to draw it out, and you can see this red arrow over here, this is 0.6 -2. If you wanted to do the same but with vector b, this point would be 4 -4. Now let's say I told you, let's add these two up. What would you do? Now, whenever we talk about operations and computations, specifically with vectors, matrices, things like that, there are two categories that you can put this in. The first category are element-wise computations. And that essentially means is, let's say you have 2, 1 plus 3, 1. What you would do is add this and this to get 5, and you would add this and this to get 2. So you're adding these two and you're adding these two, which means it's element-wise. You're taking the element at the same position in both the data and then doing some sort of operation out of them. And the other one is linear algebra computations, which are more like dot products and matrix multiplication, which follow something that's not as element-wise. So in terms of vectors, what I'm trying to say here is when you want to add, you are going to do it element-wise. So let's say you don't want to follow this graph technique. Again, this is for purely just intuition purposes, the graph, but in reality, I would not say that you should make a graph because it is pretty tedious. So let's say you had 6 - 2 plus -4, 4. What you would do is add these two and you get 2, and you add these two and you get 2. Now, how can you represent this vector of 2 and 2 in a graph? How do you even come to that? So let's pretend that these don't exist for a second. This is going one way, and this is going in a completely other way. So what you want to try and do is drag this over here, and you will get this point being 2, 2. Now, why did we drag it? Because a vector can be placed anywhere in the graph. Over here, the vector can be right here, and instead this orange arrow can be turned around this way and put over here. It can then form the perspective for where 2 and 2 should be. But the point is, in this case, because we are starting at the origin, this has to be 6 -2, and this has to be -4, 4 over here. But again, like you dragging it over here is going to be the exact same thing. It's not going to make a difference because at that point, when we're adding, we're not necessarily considering the origin. So it doesn't really matter whether it's over here or it's over here. So when you do end up adding it, you can get some sort of arrow over here, and this point should be 2, 2, as I mentioned. And that's how you do the sum. Another thing you can do with vectors is scale them, and you can scale them using scalars. You guessed it. Anyways, so multiplying a vector by scalar is quite simple as well. Let's take the white so it blends in, or it stands out from the black. Let's say you had something you wanted to multiply with 3 as a scalar and then 2 and 1. What you would end up doing is you would multiply 3 by 2 and 3 by 1, and then you would get something like 6 by 3. Now, in the real world, or not in the real world, but from a graph standpoint, let's say you wanted to map this out, and let's say we get 1 and 1 this time. So this is, well, erase this for a second because we already know the answer to this. Let's say we have this graph and we say, okay, this is 1, 1. Now let me multiply this by 3. This is 1, 1, oops, 1, 1. Let's multiply this by 3. 1, 2, 3. This is 3, 3. And as you can see, you multiplied this by 3. This would be the scalar. And so that's how you would do the scalar times multiplying vectors. And then matrices can also be multiplied by scalars. You can have the same thing here. Now for matrices, again, scalars are 0-dimensional, vectors are 1-dimensional, matrices are 2-dimensional. So they both have rows and columns. They are usually in the form of A is a set of all real numbers, and A is the matrix in this case with both capital letters, where you can say that the M represents the amount of rows and N represents the amount of columns. So these are the rows, these are the columns. An example of this is, here is a matrix that is 2 by 3, since it has, it has 2 columns and 3 rows. Oh, I think this must be wrong. It should be 3, 2. My apologies here. This should be 3, 2, and this should be 2 times 3, because we go row by column. So another thing you can do with matrices is you can transpose them, which means you can exchange the rows and columns. And this is what it looks like to transpose to go from here to here. What you're basically doing is just turning it around. And that makes it 2 by 3 instead of 3 by 2. That's what transposing it means. Now, again, matrices were two-dimensional. Tensors are like the next part of that. They're the next level. And instead of it being like 3-dimensional, it's just set as nth order arrays. So it can be n-dimensional. And especially when you're working with computer vision data or high resolution data, like brain tumors, you end up realizing that these tensors are very large. They have so many different dimensions and they become hard to work with. But there's many different things you can do with the tensor. And one of the biggest ones is obviously manipulation with like multiplication, things like that. But another big thing is sum. And usually when you want to do sum, you need to really understand the dimensionality, the different axes within the tensor, so you know what elements you're adding. Because if you have, let's say, let me not draw it out, but let's say you have a tensor that has 5 dimensions and you're adding them all up, you have to add them up in a certain way. You can't just like add them all up and expect to get a small scalar. Like that's not how it works. You add across a certain row, across a certain axis, across a certain column, and you can set that, but you would need to understand what you're actually adding in the first place. So to understand this, I have this example over here, and to understand this example, first you need to understand the shape. The shape of this is 2 by 3 by 3. How do I know this? Because you always start from outer to inner. So you start off by, you ignore this like gray bracket because that doesn't really count, but you look at the first bracket that exists. And the first bracket that exists is this bracket here and this bracket here, and you have 2 of those. Now, because you have 2 of those, you can say that the first dimension has to be 2. After that, you look at one of these specifically. So let's say we look now over here. We're going to look over here at this specific one. Now, within these red brackets that we just pointed out, what is the next brackets? And the next brackets are these blue ones. And there's how many of them? There's 3 of them. So the next dimension we would have is 3. And then we ignore these brackets again. We say, okay, let's look at one of these brackets. Okay, how many elements are here? 1, 2, and 3, separated by commas. That's our third dimension, 2 by 3 by 3. Now always start from the outer to inner, like I mentioned. So now you know the shape. How do you know that if you were to add by certain axes what you would even be adding? And what this would look like is, let's say this entire tensor is tensor x dot sum. You can do dimensions is equal to 0, 1, or 2. So you can add across dimension 0, dimension 1, or dimension 2 because we have 3 dimensions here. So if you wanted to add or take a sum through dimension 0, what would this look like? First, you would have to take the shape and you would have to take out the 2. You would say, okay, we're collapsing the 2. The 2 is non-existent because we're dealing with dimension 0. So what you would do then is you would say, okay, so we have this and we have this. How can we make these into 1 so that we only have something that's 3 by 3? What you can do is just add both of them up. So what you'd end up doing is you would add this with this, this with this, this with this, and then you would add this with this, this with this, this with this, and then you would add the last row and last row as well. And this would end up giving you something that is 1 by 3 by 3, or the same thing as 3 by 3. So you're collapsing the two, and you would get 2 by 4 by 2, 4, 6, 2, 4, 6, 2, 4, 6. Because again, you add 1 plus 1, 2, 2 plus 2, 4, 3 plus 3, 6. And then the second part is, let's say you wanted to do dimension 1. What would that mean? So now you're looking at this 3 and you're taking this one out. This 3 means you're taking out these, and you're taking out these, and you're taking out these, and you're taking out these. So the question is, let's say we're looking at only like one of these ones. How can you take these out so there's only one left? That means you would add all of these up. 1 plus 1 plus 1, 3. 2 plus 2 plus 2, 6. 3 plus 3 plus 3, 9. And as a result, you would get this when you add with an axis of 1. The last axis is axis 2. There we are. I keep erasing the wrong thing. There. Axis 2, which here would be 3. So now we ignore these. We're like, okay, now we need to ignore the commas. So the question is, how can we make, we're looking at this particular example, for example, and we're saying if we remove the commas, how can we make all of these 1, 2, 3 into 1 using sum? We add them. So you would add 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Basically get 6 times, 2 here and 3 here and 3 here for 2 rows. And so you end up getting the shape 2 by 3 by 3 here as well. And so it's pretty neat once you try to understand how the dimensionality works within all of this. Let me quickly erase this. There we go. And then you can do a bunch of other things with vectors and matrices as well that don't, and tensors as well, but most of the work that's done in a lot of machine learning has mostly just been with dot products and taking that and extrapolating it towards matrix vector products and matrix multiplication, which we'll talk about. Dot products is when you have two vectors, and to take the dot product, you have to do element-wise multiplication and then add up the elements in the same position. What this means is, let's say, I'm going to remove this for a second. Let's say you are doing dot product of this. What you want to do is element-wise multiplication first, like I said. So you would take this and take this, multiply them together, you get 0. Take this and take this, you get 1. Take this and take this, you get 2. Then you want to add them together. So 1 plus 2 plus 3, and that gives you a scalar of 3. You always end up with a scalar. And usually the dot product is used when you have a vector as the input for some sort of simple neural network, and then you have weights that determine how much of that input or what certain sections of that input need to be weighed more than others to get the output that you want. And as a result, to calculate the weighted sum of this in the neural network, in the simple one, you would do dot product. And then matrix vector products is the same thing, except maybe instead of a vector, your inputs follow matrices, and you can pretty much do the same thing. So over here, you have something that is 2 by 3, and this is 3 by 1. So what you would do here is you would take this, and you would take this, and you would find the dot product of these two, and then you would take this, and you would take this, and you would find the dot product of these two. So over here, 0 times 0 is equal to 0. Actually, I'm gonna write it like this. And then plus 1 times 1 plus 2 times 2. And that's equal to 0 plus 1 plus 2 plus 4, sorry. And that equals 5. So that's how you get that first number here. And then if you wanted to do it with this row, 3 times 0, 4 times 1 plus 5 times 2. And that equals to 14. So that's how you get the second number. And that's how you do matrix vector products. To find the end shape, what you want to find is the common number between both of them that have the same dimension. So here, usually if this is 2 by 3 and it's 1 by 3, what you want to try and do is you want to try and take this and turn it around so that this becomes 3 by 1. You want to transpose it so that when you have this and this, you can easily cancel out these 3's, and you're ending up with 2 by 1 as you did here. That's how you do matrix vector products. The next part is matrix multiplication. For matrix multiplication, you're kind of taking this concept and taking it one step further, where these are the two matrices. You want to understand how you're going to tackle them. What you do is you take, first of all, the first row in A and the first column in B, and you find the dot product of that. Then the first column of B, second row of A. Then you do the next row of A, then you do the next row of A until you reach the bottom. And then once you do that, you move on to the second row of B, and then you do the same thing. You find this and the dot product of this and this, dot product of this and this, dot product of this and this, and then you keep going in this direction as well until you've finished all the columns in B. So an example of this is over here, when you have something that's 2 by 3 and 3 by 2. And again, really be careful about the order, because this and this, even though it looks similar, they're just inverted differently. And what you tend to do is similar to what we did with matrix vectors. These middle numbers, they cancel out. So the output would be 2 by 2. So when you do 2, 3, 4, and you find the dot product of this and this is what it looks like. And you end up with getting 27. When you do the dot product of this and this, you end up getting 28. You do the dot product of this and this, you get, from here, you get 37, and then you do the last one as well. And you end up with something 2 by 2. Here, when you have something that's 3 by 2, let me erase it so it looks more neat. When you have something that's 3 by 2 and 2 by 3, you're taking these inner ones out and you end up with something that is 3 by 3. So you obviously know that it's going to be a different shape. It's going to be something different. So order always makes a difference. And this is a good example of how matrix multiplication works as well. You do pretty much the same thing. And again, you're crossing out the 3 and 3 to get the 2 by 2. That's how matrix multiplication works. There's many ways that you can tell certain properties of matrices, and people like to do this for many different reasons. For norms, it is mostly used for optimization purposes. When you have a neural network, you look at the weights that each sort of data is assigned. And when you're doing backpropagation, you are changing and updating those weights to get the most accurate possible output. With norms, you can realize that these matrices or these vectors that represent the weight, how big are these weights? When you have large weights, the problem with this becomes that even if one small change happens in terms of back propagation or forward propagation, it makes a big impact to the output of the model and the accuracy. So it's very nice to have smaller weights. And what ends up happening in terms of optimization is the larger your norm, the more you get penalized. So the model is more incentivized to have less weights. There's many ways of calculating norms for both vector and matrices. For vector, you can think of it like this. If this is the vector and these are the x, y, z coordinates, the L1 norm, and again, this is 0 to -1, 0 to 4, and 0 to 2. This is what it looks like in terms of the vector going to this part. The one norm is just adding the lengths of all these. So it's like how much distance does it take for me to go here and here through the longest path? Now there's a short path, and you can kind of think of this as the Pythagorean theorem, where you have edges of a triangle, but now you're trying to find this red line, which is the hypotenuse. And so what you end up doing is you square all of the elements of the vector, and then you end up square rooting it. After you do that, you can get the norm, L2 norm. Now, another thing you can do is the infinity norm, and that's just the biggest magnitude in elements, which is 4 in this case, even though this diagram is not scaled properly. In terms of matrices, there's the Frobenius norm, I believe that's how you say it, and that's basically the L2 norm of a matrix, where you just square root the sum of the squares of a matrices elements, and then you square root it just like with the vector. There is also a norm 1, where you just take the largest sum across columns. So you take the sum of this, the sum of this, the sum of this, the absolute value sum of this. And then you find the maximum of all the columns to see which one has the largest, and that's norm 1. And then norm infinity is the same thing, except it's with rows, so this way, instead of the columns, which are this way. Okay, I already talked about why this is important. Orthogonality is another way that somebody can tell a property of the matrix or vector, and usually it tells you the angle between vectors and matrices. So the reason why this is important is because sometimes when you want to do division of matrices, you can't. Like, that's just not how it works. So what you end up doing is you find the inverse of a matrix, and we'll talk a bit more about inverses and matrices and how they kind of represent a linear transformation when looked at visually. But in terms of orthogonality, when vectors are orthogonal to each other, it means that they're at like some sort of 90-degree angle, just like this over here. And it means that they have a dot product of 0. So when you want to do an inverse, it usually could be computationally heavy. There's like a lot of steps to do. But if you know that a matrix or a vector is orthogonal, then finding its inverse, you can just transpose it. Again, just changing the rows and columns. So it's just an easier method to do something like this. It's more computationally cheap. So I guess that's most of the benefit for why people use this. Vector subspaces, kind of looked into it, didn't seem that relevant, so I'm not going to be talking about those. Now, in terms of understanding what vectors are and what they possibly look like, you can kind of think of them as coordinates as a scalar. So a vector has 3 different values. The first value is for how far to go in terms of x. The second one is how far to go in terms of y, and then how far in terms to go for a z. And you can obviously keep on going and adding more dimensions. And another thing is, in terms of the xy coordinate system, there are these things called basis vectors. And I and j are basis vectors because they end up having this property where I is 1, 0 and j is 0, 1. I'll explain how this ties into the identity matrix, but this is just an important thing to know, is that we have these things called basis vectors, and you can scale these basis vectors too. So let's say you had something that was 1 and 0, and then you wanted to scale it by 3, right? And this is what we talked about before. This can scale this way, 3i. Now, let's say you had this and this together, where let's pretend this was a matrix, and you wanted to scale it with this to this, then you can just apply this to x, this to y, and what you end up realizing is you can scale this by 3 and scale this by -2. And from there, you can find the sum of the two scaled vectors like we did before, except now we're doing it with basis vectors. So let's say we have any two different vectors, right? And if we have different basis vectors that are not 1, 0 and 0, 1, we can choose different ones. And with the use of scalars, we can scale these vectors to go anywhere. Now, if these two scalars are linearly dependent, linearly independent, and I will talk about what that means, then it means that these can go anywhere. I mean, you can think about it, right? If this is -1, this can go this way. If this is -1, it can go this way. If you scale it this way, it can go larger, it can go this way, it can go this way. There's so, like, it can cover the entire 2D space. And this is called the span of these vectors. It's a set of their linear combinations. Now, the thing with this is, you can do this with a 2D space, but what about a 3D space? If you have two vectors that are linearly independent in a 3D space, it literally just forms a sheet. Like, let's say the Zoom screen was a 3D space. This is like one sheet formed by two vectors. Let's say we wanted to have another vector, and this time we're gonna try to increase our span. This span can only be increased if the third vector is linearly independent. And now I will be telling you what that means. So in the Coursera course, it explained it really well. A linearly dependent vector is when you have vectors that are going in opposite directions and have no correlations to each other. So an example of this in this case is when you have a non-singular vector, it could be something like this, or this could be a matrix, but let's split this up, for example, and you have 1, 1 and 1, 2. This is linearly independent because it has no correlation to each other. 1, 1 and 1, 2 have no correlation, whereas 1, 1 and 2, 2 are linearly dependent because one is a multiple of another. And so what this means in terms of, let's say, vectors is, you can kind of think of it, if let's say we were solving some sort of linear system of equations. A non-singular or linearly independent one would be like, oh, you have an arrow here and you have an arrow here, and they're like just away from each other. They're not correlated. When you have something that's singular, that's linearly dependent, they would go in the same direction. So they would go like this or like this, and that's pretty much the same. They would have infinite solutions. And that's because one depends on the other one as a multiple. Now, bringing it back to this concept, if you say, let's say we have a third vector, okay? And we have, let's say we already have two vectors that are going one this way and one this way. So it's good. You know, they're linearly independent. Now, you're adding a third vector. What if the third vector is going here? Will that increase your span? No, because it's literally sitting on the span of the first two. So the span doesn't change at all, because this doesn't really take you anywhere. It scales the same way as this black arrow was scaling before. However, if your third vector is linearly independent, and that could be, for example, this way, then the span would increase. Now, how would this span increase? Think of it kind of like this. If this is a span, and then you had some sort of vector that was actually helping with the span, maybe the span could go this way. It could go this way. It could move this way and up and down and this way and boom, 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 boom. Sorry. Anyways, that's how it could work. And then you could move around the span to get every space in the 3D space as well. So it makes a lot of sense how you could do that. Now, the next thing I want to talk about is linear transformations. And this requires understanding how matrices kind of lead to these linear transformations. Okay, and this takes us to the Coursera. So I'm going to not talk about the rank, but in terms of matrices, you can think of them as linear transformations. So let's say you had something that was here at -2 and 3. That means that it would be drawn over here. Because this matrix is multiplied to this changes what this minus 2, 3 looks like. And it makes it something like this. Now, let's say you had the basis vectors, which were, 0, 1, and 1, 0, and this formed this, and you used 3, 1, 1, 2 on this 0, 1, 1, 0 thing that 1, 0, 0, 1 thing that we had, 1, 0, 0, 1 thing that we had before, this would become, this. And so you can see how this matrix is a linear transformation to change how this area becomes after the transformation. Another thing to notice, and actually I'll talk about identity matrices after, but you can also combine linear transformations. So you can take this, apply a matrix, bring it here, apply another matrix, bring it here. You can also inverse it and bring it back, and that's what I meant by the inverse and transpose thing before. Or you could just do matrix multiplication of these two and then transform it that way. Okay. What else is important here? Okay, not much. The rank is something I'm not going to touch on either, but in terms of linear transformations, the reason why this is important is because in a lot of data sets, especially vision ones, matrices are used a lot for linear transformations. Let's say this was an image. This image can be rotated. For example, this square, pretend it's an image, it can be rotated like this. And with data augmentation, which is when you don't have that much data in your data set, the rotations or these different modifications to the data can help add more data to the original data set, which is beneficial in the long run. So that's how the matrices perform as linear transformations. Now, the next thing to kind of keep in mind are bases and eigenvectors and eigenvalues, which gets kind of complicated. Okay, so we already talked about bases, so we'll skip that part and we'll talk a bit more about eigenbases and how linear transformations work. So with the basis, let's say you start off with the identity matrix. And again, the identity matrix is actually what forms the basis vectors that we talked about, which is again 1, 0. No, I'll use this pen now. 1, 0, 0, 1. And so that's what you have here. 1, 0, 0, 1. And so when you have any matrix and you multiply it by the identity matrix, again, you get the same thing. So when you have something like this becomes this vector specifically. So you're dealing with this and this. You can see that when you want to take this and you want to compare it to this, you multiply this by 2. So what you would end up doing is, as you can see on this gray part, you multiply by 2. The same thing here where you compare, now you compare this and you compare this and you go from 0, 1 to 1, 3, which is right here and right here. As in this is 1, 3 and this is 2, 0. And so after you're done doing that, you realize that this is the transformation that happens. It goes from here to here and it goes from here to here. And then you can see that being displayed over here, where this is exactly what happens. And you can see that there's a linear transformation being applied to the identity matrix just based on this specific thing. You can see the same thing over here. Let's pick a different basis. So instead of picking 1 and 0 and 0 and 1, let's pick 1 and 0 and 1 and 1. What we do is we look at this and this together. So this and this together, and this and this together. Now, because this is 1, 0, and this was 2, 0 initially, ignore this for a second, right? Pretend that this says 0. So I'll erase it actually. So yeah, when you compare this and this, you see that you scale by 2. So this initial vector, which was 1, 0, this is still 1, 0 in the black right here. This is 1, 0. That just scales by 2. So it literally goes here, which is the gray part. Over here, this 1, 1, which was normal, right? It was literally normal. And if you wanted to calculate this original matrix, you would just have this and this and this and this. But now you're saying that this goes from 1, 1 to 1, 3. So now this, we'll draw it out. This will be 1. You can get another one. I suck at drawing, but I am doing pretty not that bad. So it would be something like that. And then you can see how it's portrayed over here as well. And then you can see how this you would say is a stretch by 2 from this side and a stretch by 3 from this side. So what you can say here is when you go through a linear transformation, the eigenvector are the vectors that are being scaled, and the eigenvalues are the values that they're being scaled by. There's a better definition over here, and I can read it out. Eigenvalues provide scaling factor, which a vector is transformed by which vectors transform when linear transformation is applied. Eigenvectors represent the directions in which the transformations occur. So that's the explanation I just gave, except that's the formal definition that I saw. And This is another example as well. This was a bit more complicated for me to understand, but the way they explained it in the Coursera course is if you had a 0.32, which is the initial thing you have, and if you wanted, they're only looking for the vector part here, because again, you're only comparing one vector to another vector, but you could also think of it as a matrix like this, where the 0, 0 doesn't really matter. It just doesn't do anything. But you can break this point into 3 different arrows, which would make it 1, 0. And because you go from 1, 0 to 2, 0, you take this and you scale by 2. So this is the value that you're scaling by. You're stretching it by the eigenvalue factor. And then you also scale 3 here, I believe, because it's actually very complicated. It's hard for me to understand how exactly they got 2 of these arrows. But what my perception was that if you subtract 1, again, this is like basically based on just intuition and perhaps some of what I learned. So you know what? I will not talk about the specific example, but what I will say is from the other examples, which are less complex, you can see how when you scale after a linear transformation, you can use the eigenvector, which are the vectors that scale, and the eigenvalue factor, which determines the stretching to form that specific thing. And then from that eigenvector, from those eigenvalues, you can also determine the x and the y that determine the scaling and like where it scales to, the vectors that it scales to, which you can calculate this. These are the eigenvectors. This is another case as well where you have like 0, 1, 0, 0, 1, and then it goes through the linear transformation by 2, 2, 3, 1. So it goes 2, 2, and 3, 1. And then you can see this is another way to think about it, where these are the vectors and the scaling factor is the eigenvalue. Another way to think about this as well, if you want to try to find the eigenvectors and the eigenvalues of this, you can see how when you see these matrices scale, or sorry, when you see this matrix scale these points, you can see that this and this is the same. It scales in the same way. So if you subtract these, they should be 0. They should be 0 because they will both be the same point, so which means that they're singular, and because of infinite points, the determinant should be 0. So usually to find the eigenvalues and eigenvectors anyways, you need to find the variables that lead to you having a determinant of 0. And so to go back to this, you can look at the equation like this. The matrix multiplication with the eigenvector over here and the eigenvector over here, this should be equal to this. And this is that, again, this eigenvector, this is the eigenvector, this is after the matrix multiplication, and this is scalar multiplication with this being the eigenvalue. So if you have any square matrix, I don't think that's relevant. So over here, you can think of it like this, right? This is exactly what this equation showed us, is AV. So with a specific matrix, when you multiply by the vector B, it is the same thing as multiplying a scalar by this vector. So you're just trying to show that's linear transformation in terms of eigenvalues and eigenvectors. So by doing this, what you can do is take this identity matrix to make it easier, and you can just replace all the ones with lambdas, because 1 times lambda is lambda anyways. And then if you take this, you realize that when you multiply, when you take this vector, and this is the scalar, so you have the scalar, this is the eigenvalue, the scalar, and you multiply by the identity matrix, you can try to get the 0 here, because the determinant has to be your 0, and that leads to the other equations. This can be taken to this side of the equation. And so, again, when you get this equals to 0, you can, this is the equation. You can find the determinant where this would lead to this being 0. The way you can go about doing this, and this is where it talks about over here, is what you need to do is try to tweak this as much as possible so that the determinant turns into 0. It's like turning a knob, where if this is the determinant currently, how can you change the factors within the matrix so that based on the eigenvalue, you can get a certain determinant that makes it 0. And so as the lambda changes, the matrix itself changes, so the determinant changes to try to get itself closer to 0. So what you do here is you just take the current like matrix that you have, and you just do minus lambda on all the diagonals, and then you find the eigenvalues, you substitute that, you find the eigenvectors, and that's how you would deal with the eigenvalues and eigenvectors. I don't know how well I explained that, but I think it might make sense more in my head, and it just takes more time to articulate, and it takes me more time to actually process it. But hopefully that was somewhat helpful, and hope you enjoyed the video.